in chemistry, one of the things that we think about are chemical changes, or another word for this is a chemical reaction. So in a chemical reaction, you have a starting substance or substances, and these things react to form something new. Now, I could express it in words. I might tell you hydrogen can react with oxygen to make water. So that would be just using words to describe a chemical change or reaction. But oftentimes, chemists find valuable information, and a valuable tool for communication is a chemical equation. So all a chemical equation is, it's when we use formulas of our substances to describe the reaction that is occurring. So chemists use chemical equations quite a bit. Now in the general format, and you can see it right here, here's the general format of a chemical equation. We have the reactants, which are our starting substances. You might think about this as the chemicals that are on the lab bench. And then we have this arrow here in the middle, and the arrow indicates to us that a process is occurring, something's being made or formed or something's happening, and then we make products, which are the new compounds formed. So you can see we start with our starting substances on the left-hand side of the equation, called the reactants, and then on the right-hand side of the arrow we put our new substances that are formed, and those are called our products. So right here below, I have written a general equation, and this equation doesn't really mean much to us right now. I just want you to get the idea of how an equation would look and how we associate it with the words that are here. So we have here on the left-hand side of the arrow, we have the reactants. See right there is the arrow that's telling us that we've made or formed something. And on the right-hand side of the arrow, we have over here our products. So here we've used chemical formulas. It says this is methane right here. And then you'll notice that this is a G. Oftentimes, it's not required, but oftentimes they'll put the state of the substance that's reacting or being produced in parentheses after its chemical formula. So this is something that makes sense. So over there I have G, which would tell me that it was a gas. An L would tell me that that substance was a liquid. S would tell me that it was a solid. And then oftentimes you'll see an AQ, which means aqueous, which means it's been dissolved in water. So a lot of the solutions that we use are actually solids dissolved in water, and we want the solids as part of our reaction. So if there's AQ behind it, it simply means that substance was dissolved in water. Other things we see, so back to our equation. So here, this is, I told you, methane, and it's a gas, and it's reacting with oxygen. And then you might notice over the arrow there's a little triangle. Well, the triangle is a way, it's called delta, and it's one way to express that heat had to be added to this equation. You might find other things over the arrow, and it's just about giving more information. For example, if a catalyst is required, that might be written over the arrow. Now this reaction you see produces carbon dioxide gas and some water vapor as well. Now another part of this equation that might be have caught your attention are these numbers in front of some of the formulas. There's two of them in this particular equation. There's two twos. And these are what we call coefficients. And they're the result of a balanced chemical equation, which we haven't talked about yet. But all of our equations will have to be balanced. And as a result, sometimes you will have whole numbers that are placed in front of the formula. And we'll learn more about that. Now notice, for example, in front of this is methane, there's no number. Well, when there's no number, kind of like in a formula, it's assumed that it is a 1. So it's not written there that it's a 1, though. I'm going to go ahead and erase it since it's not written. not written. Sorry, I was having trouble with the eraser. So that just gives you an idea of what's there. Reactants to the left of the arrow, products to the right of the arrow. You have chemical formulas depending on what reaction you have. You may or may not have the states in parentheses following the formulas. And then if it's a balanced chemical equation, which they'll need to be balanced, you'll have coefficients or numbers. So when I talk about balancing, this may be the first time you've heard of balancing. There's a natural law we need to consider called the law of conservation of mass. So basically the law of conservation of mass says that matter, atoms, cannot be created or destroyed during a chemical reaction. So what happens is when there's a reaction, whatever atoms we begin with, those same exact number of atoms have to be there when we finish. So you might say, well, what's going on then in a reaction? Well, in a chemical reaction, in the reactants, bonds are broken and new bonds form. And in that process of new formation, the atoms rearrange to form new substances. So while we have the same number of each type of atom on both sides, the difference is they've rearranged, and some bonds have been broken and some new bonds have been formed. So we don't have the same chemicals before and after. Another way to think of the law of conservation of mass is that the mass of the reactants would always have to equal the mass of the products. Now, sometimes in everyday life, we may think that we violated the law of conservation of mass. For example, if I had a large log and I burned it in a fire pit, and if I measured the mass before and then I collected the ashes and measured the ashes after, I might think, well, the mass isn't the same before and after. But oftentimes, like in that example, if any of the products are gaseous or gases, they go into the air if you don't collect them. And so really, we're not collecting all of the mass of the reactants and comparing it to all of the mass of the products. If we had a closed system where nothing could escape, we would see that it's always true, the law of conservation of mass, that the mass of the reactants equals the mass of the products. Now this law is what we use to balance chemical equations. So down here I have just a chemical equation where this is nitrogen reacts with hydrogen to make NH3 right here, which is ammonia. Now when I compare, so here's the arrow, so I know that it's the reactants to the left and the products to the right. And if I compare how many atoms I have based on what I've written here, we'll see that this equation is not balanced. So if I look at this nitrogen, there's a 2 there, which tells me I have 2 nitrogens. And then here's a hydrogen, and there's 2 right there. I have 2 hydrogens. So on my reactant side, I have 2 nitrogens and 2 hydrogens. Now if I look at the product side, so I'm looking at this right here. Well, the nitrogen, there's only 1 of them. So I have 1, but the hydrogen now there's 3 from the formula. So there's 3. So let's looking at these numbers. So on the reactant side, I have 2 nitrogens and 2 hydrogens, but on the product side, how it's written, I have only 1 nitrogen and 3 hydrogens. So it looks like miraculously one of the nitrogens turned into a hydrogen, and which in a chemical reaction, this cannot occur. So what we consider, this is not telling us everything, what we consider is that this equation is not balanced. When it's not balanced, how it's written, it does not follow the law of conservation of mass. Now, since this is a natural law, we have to follow it. And so how we do that is by balancing equations. And this is where we get the coefficients. So let's look at this next equation. And this one you can see down here I've already identified as balanced. So what the difference is, if you look on the balanced equation, I have coefficients in front of these. So this is already balanced. On the next slide, we'll learn how to balance. But right now, I just want you to understand the difference between something being not balanced and something being balanced. So the second equation is the same chemicals, nitrogen and hydrogen, to make ammonia, NH3. But in this case, when I compare, when I add the coefficients, it's balanced. So still on this side, when I'm looking at nitrogen, there's a 2 next to it. So there's 2 nitrogen. Now this time with hydrogen, there's still a 2 here. But when you put a coefficient in front of it, you multiply it. So 3 from here times 2 here, 3 times 2 is 6. So we have 6 hydrogen atoms because I added the 3. I wanted to erase it so we can see it better. Now this, the second half, the product side, there's a coefficient of 2. So 2 times 1, that gives me 2 atoms of hydrogen. And then 2 times 3 gives me 6 atoms. 2 atoms of nitrogen, and then 6 atoms of hydrogen. So now comparing, when I count both sides, I see that both sides have 2 atoms of nitrogen, and both sides have 6 atoms of hydrogen. So by adding the coefficients, and I'll erase it so you can see it more clearly, by adding the coefficients of a 3 and a 2, I have created from I have gone from an equation that is not balanced right here, and I've created a balanced equation. So by adding the coefficients, it's now considered balanced. And if it's balanced, it follows the law of conservation of mass. So how do we balance? So basically, balancing a chemical equation is relatively there's very little we can do. There's only one thing we can do, and here is the rules. We're going to use, or you could think of it as add coefficients. So coefficients, if you remember from the previous page, these are going to be whole numbers. And we're going to place these whole numbers in front of the formulas. Now, what's going to motivate us is right here, the second part, so that the number of atoms of each element is equal on both sides of the equation. So the number of each type of atom on the reactant side is going to equal the number of each type of atom on the product side. Now look, all I can do right here is add coefficients. I may not change the formulas. Okay, I'm going to write it here because this is common. You think, oh, I need 3 oxygens, so you erase whatever number is by the oxygen, like you would erase it like that, and you would just write a 3. Okay, that is not allowed. You cannot change formulas. You also must write the coefficient in front of the formula. So see down here on this water example, if I needed to put a 2 in front of it, I cannot just add a number in between the hydrogen and the oxygen. That is not allowed. So the only thing I can do is place numbers in front of the formula. And if I place a number in front of a formula like I did down here that has multiple things, this number will multiply through to each element in the formula behind it. So these 3 examples all do come from your textbook at one place or another, and I have them on. I have several, like 5 different ones we're going to practice. So I'm going to turn this page and we'll see what try to put this in action. Okay, so here was the first equation. Now what I like to do is kind of set up a table. This is not required. Some of you, as you get better, will balance by what's called inspection. So just by looking back and forth and comparing. But when you're first starting, sometimes it helps to have something written down. So I always I draw a line here where my arrow is, and that separates. So on the left-hand side, I want to compare these reactants to the elements on these products. Now, I like to list my reactants. So I say I have aluminum and oxygen, or list my elements, they're on both sides, aluminum and oxygen. Now, I have found through experience that while order is not, there's not a specific order that's required, that if you balance, if you do the metals first, oh, sorry, I hit the wrong button, metals first, and then if you do non-metals, and then you do hydrogen and oxygen, this tends to be the path of least resistance to balancing. But I will tell you that if you come across an element that you're trying to balance, and it's particularly difficult, you can actually skip it, go to the next element, and come back. So the order is not key in balancing. Now, one thing that is key is I want you to balance one element at a time. So don't try to fill out. I have a little chart here. Don't try to fill it all out before you start. Let's just start with one element. So I'm going to start with aluminum. So I go to this side and I see there's only one aluminum, so I just write a 1. And I go to this side, here's my aluminum, and I see right here that there's 2, so I put a 2. So looking at that, it is not balanced. Let me erase this. I'm trying to show you how I'm thinking. And so that's not balanced because I have a 1 and a 2. So now I'm going to add the coefficient. If I put a 2 here, 2 times 1 gives me 2. So that balances because now I have 2 on both sides. So then, sorry, I erased my answer. This was Al2, my products, O3. So then now I go to the oxygen. So oxygen, I look here, has 2. And this oxygen has 3. Okay, so the first number, remember I can multiply to make these bigger. The first number that they have in common is 6. So if I put a 3 in front of this, 3 times 2 is 6. And if I put a 2, you have to put it in front of the whole formula. 2 times 3 is 6. Now you may notice here that by putting the 2 in front of this one right here, in front of the aluminum oxide, I changed my aluminum. So I have to go back and fix it. And 2 times 2 is 4. And then that means I will erase this 2 because it doesn't work anymore and put a 4. So now looking at this equation, I have 4Al plus 3O2 makes 2Al2O3. And that equation is balanced. So let's try another one. And I recommend that you pause here. I'm going to keep working, but you pause, then you can try it yourself and see how you do. So if I'm going to go through the whole steps, I kind of draw a line here. I'm comparing reactants to products. You would not have to write everything. I just want you to see how I'm thinking about it. Then I have, this one only has hydrogen and oxygens. Now I balance one thing at a time. So I'm just focusing on hydrogen now. I don't have to focus on oxygen. So on this side I have 2, and this side I have 2. So if they end up being the same, you don't have to do anything. And there's actually equations where the coefficients are all 1 and it just is balanced. But hydrogens are balanced how it's written. And now I go here, there's 2 oxygens, but on here there's only 1. So that's not balanced. So I'm going to, sorry, I wanted to show you, I'm going to put a 2 in front of this, so now it's 2 times 1, so that equals 2. So now if I compare these two, I've balanced. Now, anytime I add a coefficient here, that 2 doesn't only affect the oxygen, it also affects the hydrogen. So adding the 2 made the hydrogen go up to 4. So now looking at these two, it's not balanced, but I can get this number up to 4 by putting a 2. So 2 times 2 is 4. So then I have it balanced. It's 2H2 plus O2, I didn't add anything to that one, makes 2H2O. Really, in words, what I'm thinking is 2 hydrogen molecules would react with 1 oxygen molecules, and from that I would get 2 water molecules. See, the coefficients are giving me information about the chemicals that are reacting. So here's another one, and it looks quite daunting, but I think if you break it down, you'll be okay. So if I think here in the middle, so I'm going to do metals first, sodium, followed by nonmetals, sulfur, phosphorus, followed by hydrogen and oxygen. Now those of you who are more experienced, you can balance by keeping the polyatomic ions together. Do you see here is a sulfite, and here is sulfite, and here is phosphate, and here is phosphate? You can actually keep those together as a group, and so it saves a little bit of time when you're balancing. But I think for the sake of this introductory video, I am just going to look at each individual element. Okay, so now let me think about this balancing. So I start with sodium. So there's a 2 here, so I have 2 sodium, and there's a 3 here, so I have 3 sodium. I compare, they're not the same, so 6 would be the first one in common, so I put a 3 here, that's 3 times 2, so that's 6, and I would put a 2 here, so that's 2 times 3, and that's 6. So now I'm balanced, check. Now I'm going to do sulfur. So there's a sulfur here, and there's only 1 in the formula, but I have this 3, so it has to go to everything. So 3 times 1, there's 3 sulfur. And here's the sulfur here. This is a 1 right now, so it would just be 1. So in order to balance it, I would put a 3, so now it's 3 times 1. Comparing, it's balanced. Now I'm going to go to phosphorus. It's okay if I skip the other one. So on this side, there's only 1 phosphorus. On this side, there's only 1 in the formula, but there's a 2 here. So 2 times 1 gives me 2. So comparing, they're not the same. So I need to put a 2 in front of the formula. See, then it's 2 times 1. So that would be 2. So check, check. Now hydrogen. And I have a lot of writing here to try to show you, but you wouldn't necessarily have to write everything. Hydrogen, there's a 2, and then it has to be times a 3, so there's 6. And here there's a 3 times a 2, so there's 6. So check. Now I have to be honest here. If my oxygens do not balance, I'm going to be disappointed, because if they didn't balance, I would have to go back and change everything. If you find yourself getting in a continual loop, please reevaluate and make sure you've written everything correctly, because you shouldn't get into a loop you can't get out of. So my oxygens, I have here's a 3, so I have 3 times 3, which is 9. Plus, there's oxygens right here too. That's 2 times 4, which is 8. So that's 17. And here I have 3 times 3, which is 9, plus 2 times 4, which is 8. So that equals 17. So it balanced. So rewriting the equation without all the scratching. So we have, oops, sorry. I apologize. So I think I'll write it on the bottom. We have 3Na2SO3 plus 2H3PO4 makes 3H2SO4 plus 2Na3PO4. So in this particular reaction, every substance had a coefficient. Okay, so let's try one. Again, feel free at any time to pause and do it on your own. I would separate it. So I have K, Cl, and O. So I have one thing at a time, and 1. Cl is 1 and 1. O is 3 and 2. So up to this point, I was balanced. But now I'm going to have to change it. So let's see, a 3 and a 2 is going to be 6. So 2 times 3 is 6. And a 3 times 2 is 6. But now I changed it by adding the 2. So now I have 2 KCl's. So put a 2. And that would be 2 here. And then 2 times that, that's 2 chlorine and 2 chlorine. So that balance, I had to go back and add a 2. So let me rewrite it, and you can try it too. It's 2 KClO3 goes to 2 KCl plus 3O2. So let's do one more equation. And hopefully you're getting the idea. There's plenty to practice, so you can look around for some practice problems. So let's see on this one. So I have sodium, hydrogens, and oxygens that I'm going to work on. So sodium 1. Hydrogen, I have 1 here, plus over here there's 2 more. So I have a total of 3. You have to add all of them. And on this side I have hydrogen, which is 2, plus 1 more here, which is 1, so that's 3. So far this is balanced, and sodium and the hydrogens. Now let's look, this is probably going to be our trouble spot. 1 oxygen on this, and 1 oxygen on this one. Okay, so here's an example of an equation that did not need any coefficients to be balanced. So let me try another one. I would like to do one more. Okay. So there was an example. Remember I told you sometimes there's ones that don't need to be balanced, or they're already balanced. So what do I have here? Copper, nitrogens, and oxygens. This one just looks hard. Let's see. So I have 1 copper on this side. Remember the 2 will only go in the parentheses. And 1 copper. So far so good. Now here's a nitrogen right there, and because there's a parentheses, that 2 is going to distribute in. So there's 2 nitrogens, and on this side there's only 1. So I'm going to put a 2 in front of that, so that would make 2. Now the oxygens, 2 times 3, there's 6. And here I have 1 plus 4 plus 2. So what is that? Oh, it's 7. Okay, so I have 7. So this is a challenge. These are ones that can be challenged, and I'm going to show you a trick, and you might be able to figure it out without the trick, but I'm going to show it to you anyway. So looking at this oxygen here, like it's hard. there's not a way to get 6 into 7. So there's a couple ways you can approach this. And what I'm seeing myself is I do not want to add a coefficient here or change this coefficient, because if I do that, I change everything. So what I want to do is I'm going to add a coefficient to this guy right here. So I think to myself, instead of having a 2 here, right, I really wish that was just a 1. Right? That's what I want it to be, because then it would be 1 plus 4 plus 1, and that would be 6. So I'm going to do something crazy. I'm going to use a fraction. So if this is a 2, if I put a fraction 1/2 here, you can use fractions. You'll see how I have to fix it. So what this would say is 1/2 times 2. And that equals 1. So that would change this to 1, and that would be 6, and that would be balanced. So I would have a 1, a 1, a 2, and a 1/2. Now here's the deal. In balancing equations, we can't leave fractions. So if I was in math and I wanted to get rid of that 1/2, what I would do is multiply everything by the denominator, or 2. So then I would end up with, I'll write it up here at the top, 2 CUNO3 2. Then I have to multiply by everything, so it would be a 2 CUO plus, now it's 2 times 2, 4 NO2 plus just O2, because 1/2 times 2 is 1. So now let's see, now let's check it. 2 times that, I have now 2 and 2, balanced. Then the nitrogens, I have 2 times 2, which is 4, and 4. And the oxygens, I have 6 times 2, which is 12. And here I have 2 plus 8 plus 2, which is 12. So this one, you just witnessed the trick of using a fraction to balance equations. And I end up with, if I rewriting it, I'll kind of write it in the middle. I ended up with this equation. Now this is definitely a more challenging one, so you think about it and process it. Here's the equation. But it's worth a second look.